Hello. In this video, we want to review some of the concepts related to congruences. So we define what is congruent, what does it mean for A to be congruent to B mod n, and then we review some of the properties of this relation, and we get to the arithmetics of mod n integers modulo n. Okay, so let's start with the set of integers. So the set of integers is denoted by this notation z. And for every a and b, for every integers a and b, we say a divides b, or we say b is a multiple of a if b is a times some other integer k. And we denote this by this notation, that a line b, and we say that a divides b. Now, suppose n is a non-zero integer. Then we define this congruence relation. We say a is congruent to b modulo n, and we denote it by this notation over here. A is congruent to b modulo n. Or we simply write it like this, that a is congruent to b mod n. So this point of view gives more indication of equality of a and b through the angle of mod n. So we write it like this: if a minus b is a multiple of n. So if you think about a clock with numbers 1, 2, 3, 4, ... but if there are only n positions on this clock, then a and b will be on the same spot. So essentially, they are giving us the same point on a circle that has perimeter, that has length n. So I give you this circle, so where is it? So I give you this circle, so let me see. And I tell you that this circle has n spots on it. So I start with 0, then go 1, then go 2, and I go like this, and I reach to n minus 1, and then again n will be on top of n will be on top of 0, n plus 1 would be on top of 1, and I continue like this. So as you can see, if I continue like this, then a would be congruent to b modulo n precisely when a and b would be on top of each other on this circle. Okay, so now one of the things that we want to show about this relation, we want to recall about this relation, is that it is an equivalence relation. So this a mod a is congruent to b mod n gives us an equivalent relation over the set of integers. Okay, what does that mean? What should we show? A relation is an equivalent relation if it satisfies three properties. It is reflexive, it is symmetric, and it is transitive. Let's start with reflexive. In order to show that this is a reflexive relation, we need to show that every integer a is in relation by itself with itself. This means we need to show that a is congruent to a modulo n. That's equivalent to saying that we need to say why a minus a is a multiple of n, which is the case because a minus a is 0, and 0 is multiple of every other integer because n times 0 is 0. So from there, I deduce that a is in relation to itself, which means this congruence relation is indeed reflexive. Now, why is it symmetric? What does that mean? This means we have to show that if a is congruent to b modulo n, then b is congruent to to B, then B is congruent to A modulo N. So let's start with the hypothesis. So A is congruent to B modulo N. What does that mean? It means the difference of A and B is a multiple of N, which means A minus B is N times K for some integer K. Now, I'm interested in whether or not B is congruent to A modulo N. But B is congruent to A modulo N if B minus A is a multiple of N. From this equality, we easily see that B minus A is N times minus K. And minus K is also an integer because K is an integer, and negative of an integer number is also an integer. So from here, I deduce that B is congruent to A modulo N. So the congruent relation is a symmetric relation. Finally, I want to discuss why the congruent relation is transitive. What does that mean? It means I have to show that if A is congruent to B modulo N and B is congruent to C modulo N, then A is congruent to C modulo N. This is what I need to show. Again, let's start with hypothesis. A is congruent to B modulo N means that A minus B is a multiple of N. N divides A minus B, which is equivalent to saying that A minus B is N times K for some integer K. Now, what is the other assumption that we have? We also know that B is congruent to C modulo N, which is the same as saying that N divides B minus C. That means B minus C is N times L for some integer L. Now, we are interested in showing that A is congruent to C modulo N, which means I need to show why A minus C is a multiple of N. Now, from here and here, I need to reach to A minus C. How can I do it? I can simply add these, and then B and negative B cancel out. I end up getting A minus C. So as I add these two equalities, the left-hand side of the equalities give me A minus B plus B minus C. And as I pointed out, these two cancel out. I end up getting A minus C, which is a good sign. And on the right-hand side, I get NK plus NL. And I can factor out N, and I end up getting that it is N times K plus L. But notice, K and L, both of them are integer numbers, and therefore their summation is an integer number, which means A minus C is an integer multiple of N. And therefore, it's a multiple of N, which means A is congruent to C modulo N, as we wanted to show. So altogether, we deduce that this mod N relation is an equivalence relation. Now, we've seen these two other points of view for any given equivalent relation. Whenever I give you an equivalent relation, it comes with a partition and a type of property that classifies our equivalent classes. Okay, so let's go through that. Let's recall the partition that we get out of an equivalent relation. So every equivalent relation that I give you, it gives us a partition and an equality function, a property as I call it. Now, what is the partition? The partition comes from the equivalent classes. The equivalent class of A the equivalent class of A, of an integer A, with respect to this congruence mod and relation is called the mod and residue class. So from this point on, we will refer to this equivalent class of A with respect to the mod and relation. We refer to this as the mod and residue class of A. And if n is clear, we just simply refer to this as the residue class of A. And this is denoted by, similar to the general setting, as a square bracket of A, but this time sub n. With this sub n, we are indicating that I'm using this mod n relation. So square bracket A, square bracket, closing square bracket sub n, denotes the mod and residue class of the integer A. So point out, let's emphasize that this is indeed a subset of set of integers. For instance, if I look at residue classes mod 2, and then I look at the residue class of 0 mod 2, this is nothing but even numbers. And residue class of 1 mod 2 is nothing but odd numbers. Okay, but what do we know from the general rule that we know, the general fact that we proved about about equivalent classes? We showed that given an equivalent relation, equivalent classes form a partition of my set, of the given set. Therefore, the residue classes form a partition of a set of integers. So the set of all the residue classes is a partition of the set of integers. Moreover, we showed that A is related to B if and only if the equivalence class of A is the same as equivalence class of B. This is a general rule that we proved for any equivalent relation. In particular, in our setting now, we get that A is congruent to B modulo n if and only if the residue class of A, the mod and residue class of A, is equal to the mod and residue class of B. We will be using this again and again later to translate questions about residue classes to questions about integers mod n, to congruence questions. So this way, instead of working with residue classes, we will be working with questions on congruence relations of integers. It would be more concrete to work on this side, but it would be more conceptual to work on this side. We will be asking interesting questions on this side, and we'll be answering them using the other side. Most of the times, but from this point on, from some point on, this side itself can give us very good ways of answering some questions and contributing to the other side. Okay, so this partition that comes from mod and residue classes is denoted by z sub n. Okay, in order to understand this z sub n better, let's start with one observation. So I want to understand this partition better. So this means I want to pick an integer A, and I ask myself, what can I say about the mod and residue class of A? Okay, so I pick an element and I ask myself, okay, so what happens if B belongs to this mod and residue class of A? By definition, this means that B is equivalent, is congruent to A modulo n, which is equivalent to saying that B minus A is a multiple of n. That means B minus A is n times k for some integer k. So because I'm interested in B, let's put negative a to the other side. that means that B is of the form A plus nk. So that means B belongs to this mod and residue class if and only if B is in this arithmetic progression, having A in it with increment n. But I go from to both sides. I add n or subtract n, starting from A. So mod and residue classes are nothing but arithmetic progressions with increment n. So these are all the mod and residue classes. Okay, but how many elements do we have inside this Z sub n? In order to understand this better, how many elements Z sub n has, we have to recall the long division property of integers. And in order to say the long division and more about the set of integers, we have to recall an important property of the set of positive integers. The set of positive integers has this property that we call well-ordering principle. The well-ordering principle can be viewed as a kind of axiom that we assume that the set of integers have. So, okay, what is this well-ordering principle? So our next goal is to recall what is the well-ordering principle, use it to prove long division, and then after proving long division, we'll come back to the set congruence relations and the set of integers modulo n. By the way, this again, maybe I did not say it, I went quickly through this. This set of partition that we denote by Z sub n, we call it the set of integers modulo n. Okay, so we want to understand the cardinality of the set of integers modulo n, and we get to this after we prove long division, and using that we show that in fact the set of integers modulo n has exactly n elements. Okay, so let's start with the well-ordering principle. As I pointed out, it's an axiom, and so the statement is quite easy. This can be written either for non-negative integers or for positive integers. Both ways are okay. So here I wrote it for non-negative integers, but it can be equivalently written for non-negative integers. So what is it? It says that every non-empty subset of non-negative integers or positive integers has a minimum. Okay, it's rather easy, intuitive, because I start from, let's say, 0, 1, 2, ... If I give you a non-empty subset, then it has an element. Then the integers that are non-negative integers that are less than that element, there are only finitely many of them. So only finitely many of them can belong to this non-empty subset that I'm giving you. From there, we can deduce that there should be a minimum inside this set. But I mean, this one has to be extremely careful. What are the integers? How can I actually define them? So it gets into the realm of set theory. So we take this for granted. We assume that this is correct, that every non-empty subset of either non-negative integers or positive integers has a minimum. This is called the well-ordering principle. This is an important statement. Using this, one can prove the induction principle, one can prove a long division, and so on. Okay, so let's use this to prove long division. What is long division? Let's start with the statement. Statement says that if I give you two integers, a and b, let's say b is non-zero because I want to divide a by b, then indeed I can divide a by b, get a quotient q and a remainder r, so that a is b times q, b times the quotient, plus the remainder, and the remainder, being the remainder, is non-negative, and at most strictly less than absolute value of b. So intuitively, let's start with a pictorial argument to get a feeling about this statement. We start with a rectangle, a by b rectangle. Here I'm assuming both a and b are positive. So I start with a by b rectangle and I start cutting this rectangle, making it smaller and smaller. Each time that I cut it, I cut a square, a b by b square from this rectangle. So I cut one square. If I can, I still cut another square b by b, and I continue like this till I cannot cut a b by b square anymore. That means I'm gonna get, the remaining rectangle doesn't have enough space for me to cut another b by b square. So we end up getting the remainder, which is r times b. Then the number of squares that I've cut is going to be my quotient. So here in this picture, I have 4 b by b squares. So that means my quotient would be 4. And my remainder, of course, depends on what a is, but it's definitely this length. Okay, that's the picture that we should have in mind. So what does that mean? This means that I'm looking at subtraction of a by multiples of b. I subtract 1b, 2b, 3b, 4b. I continue like that till I cannot do it anymore. That means the remainder is the smallest non-negative integer among all the elements in the arithmetic progression a minus bk. So we subtract first b, second b, and so on till I cannot do it further. That means I'm getting to the bottom of this among non-negative integers. I don't want to pass to negative integers. I just want to work with this rectangle. So I don't want to get a negative number. So that's the idea. And let's now make the formal proof. And here I have to be slightly more careful as well, as I'm not assuming that a and b are positive integers. They can be negative. So that's why I need to take care of this by putting absolute value and so on. But the general idea, the pictorial proof, is already in this rectangle and cutting it, cutting these squares one after another. Okay, but let's use this idea that we got out of this, that we have to focus on the smallest non-negative integer among the arithmetic progression that is of the form a plus a multiple of b. Okay, so as we have discussed, this arithmetic progression is nothing but the residue mod b residue class of a. So that's the same. I'm just using it as a notation. Here we don't care that it comes from this residue class, but I'm just using it as a short symbol for the arithmetic progression of the form a plus a multiple of b. Okay, so as I've indicated, we are interested in non-negative integers inside this arithmetic progression. So let's call the set of non-negative integers inside this arithmetic progression sigma. So sigma consists of non-negative integers that are inside this arithmetic progression, which means it's the set of all the elements of the form a plus bk, where k is an integer, and a plus bk is non-negative. So that is my set sigma. Now I want to use the well-ordering principle for the set sigma and say that sigma has a minimum, and that would be my remainder, because that is our intuition. Our intuition says that the minimum of sigma should be our remainder. But how do I know it has a minimum? I want to use the well-ordering principle. In particular, I need to say that sigma is not empty. Okay, what does that mean? I start with an integer a, and I give you another integer b. I either add or subtract this other integer b to a again and again and again, and I want to say that at some point I get two non-negative integers. Okay, so how can I make sure that this is the case? Because b is not 0 and it is integer, the absolute value of b is 1. So each time that I add or subtract this b, I'm actually changing it by quite a lot of amount, at least one step. And one thing that I make sure of is that because absolute value of b is either plus b or minus b, I can either add or subtract b and make sure that I'm adding absolute value of b at each step. So I'm starting with a, adding absolute value of b one time at a time, one after another. And if I do it absolute value of a times, for sure I'm going to get to the positive side. Let's see why this is the case. Absolute value of b is at least 1. That means absolute value of b times absolute value of a is at least absolute value of a. Now, if I add a to both sides and go one more step, so I add one extra absolute value of b, so I'm adding a total of absolute value of a plus 1, and then I add the initial point of this arithmetic progression, which is a, and then I notice that this first term is at least, okay, so this product is at least absolute value of a, this 1 gives me an extra absolute value of b, and then I'm adding a, which might be negative, but nevertheless absolute value of a plus a is definitely non-negative. If a is negative, I get 0. If a is positive, then I get further. If a is 0, I still get 0. So this is definitely non-negative. So altogether, I get that it is at least absolute value of b, which is positive. So this number, whatever it is definitely positive. But at the same time, it is some integer multiple of b with either sign, plus sign, or negative sign, plus a, which means it is in the arithmetic progression starting with a and adding or subtracting multiples of b. So I'm getting something in the arithmetic progression that I'm interested in, and it is also positive. So it's definitely a positive number inside this, which means sigma is not empty. Okay, this shows this claim. Now I can use the well-ordering principle. Because sigma is not empty, by the well-ordering principle, it has a minimum. Suppose r is the minimum of this sigma, which means r is the smallest non-negative integer in the arithmetic progression that has elements of the form a plus or minus multiple of b. Because r inside the sigma, r itself is of the form a minus, I'm using minus, but q can be negative as well, so there is no restriction here. So r is a minus a multiple of b. So for some integer q, r is a minus bq. Notice that I can rewrite this and say that a is bq plus r. That's why I wrote it like this, because now this is exactly what we wanted. This is exactly what we needed over here. Now I want to make sure that the other condition also holds. R indeed is a remainder. This is what we want to show, and that's the second claim, that R is strictly less than absolute value of B. Notice that R is inside sigma, so already it is non-negative. Sigma only has non-negative integers. So the lower part, the lower bound of R is already there. We already know that R is non-negative. Now I want to get the upper part, in order to get the conditions that we want. So this part is already fulfilled. I want to say that R is a remainder. That means that it's strictly less than absolute value of B. Now, in the pictorial picture, what does that mean? This means if it was not like this, then I should have been able to cut another B. I should have been able to cut another square out of this rectangle. That's exactly what we are going to do. We are going to assume that R is at least absolute value of B and say that, then it could not have been the minimum inside sigma. I can find, in that instance, I can find another element inside sigma which is smaller than R and get a contradiction out of that. I want to cut another square out of this rectangle. That's what I'm going to do. Which means what? Which means I'm going to look at R minus absolute value of B. Because absolute value of B is a positive integer, this is indeed smaller than R, strictly smaller than none. But by the contrary assumption, it is also non-negative. So it's a non-negative integer. And R itself was of the form A minus BQ. It was in this arithmetic progression. When I subtract absolute value of B, I'm still inside this arithmetic progression. Because either I'm adding or subtracting B. In either case, I'm not leaving the arithmetic progression that has increment B. So R minus absolute value of B is still inside this arithmetic progression. It is non-negative, therefore it is inside sigma. Sigma consists of non-negative integers inside this arithmetic progression. And R minus absolute value of B is both non-negative and inside this arithmetic progression. This is a contradiction because R was supposed to be minimum among the elements of the sigma. Now we found this guy, which is even smaller than R. And that gives me a contradiction. Now, what does this contradiction imply? It implies that R is strictly less than absolute value of B. Now, altogether, I get at least the existence of the desired pair of integers Q and R. Now, we found this pair of integers Q and R so that A is BQ plus R, as I have pointed out, and R is non-negative because it is inside sigma, and R is strictly less than absolute value of B, as we proved in claim 2. So I get all the desired relations for the pair of integers Q and R. Next, I want to argue why this pair is unique. So there is a unique pair of integers Q and R with these properties that we have over here. What does that mean? We are going to assume that Q comma R and Q prime comma R prime, both of them satisfy these conditions. Next, from there, we show that Q is Q prime and R is R prime. Therefore, there is a unique pair of integers with these properties. Okay, what does that mean, that with these properties? It means A is BQ plus R and BQ prime plus R prime. Moreover, both R and R prime are supposed to be remainders, which means they are non-negative integers and strictly less than absolute value of B. Now, from here, I can take the terms that have B in them on one side and remainders to the other side. So from this equality, we deduce that B times, and then I factor out this common factor B times Q minus Q prime is R prime minus R. Okay. Now I want to involve these inequalities, which means I have to pay attention to the absolute value of these guys and see how large they can be and compare it with the other side. Let's first focus on this side. R and R prime are two integers. Both of them are in this interval from 0 to, in fact, absolute value of B minus 1. So both R and R prime are here. I don't know which one is larger, which one is smaller, or they are equal. I want to show that they are equal, but they are in there. That means that the distance between them is definitely at most the length of this interval, which means absolute value of b minus 1. So the distance between them, which can be captured by the absolute value of their difference, should be strictly less than absolute value of b. So this is what we get from this picture. Now I'm going to give you a bit more details on this. So R is a number which is non-negative. Therefore, R prime minus R is definitely at most R prime because I'm subtracting something non-negative from it. And R prime itself is an integer which is strictly less than absolute value of b. Similarly, R prime is a non-negative integer. Therefore, R prime minus R should, we are shifting minus R by something non-negative, should get something larger than negative R, and that negative R is strictly more than absolute value of b. So this difference, R prime minus R, is strictly less than b, absolute value of b, and is strictly larger than negative absolute value of b. Therefore, the absolute value of this quantity is strictly less than absolute value of b. Okay, let's write it. So altogether, we deduce that absolute value of R prime minus R is strictly less than absolute value of b. But why did we do that? Because we knew that this difference is a multiple of b. But how can that be? I have a non-negative integer, which is a multiple of b, which is a multiple of absolute value of b, but at the same time, it is strictly less than absolute value of b. So this means that this product is strictly less than absolute value of b. Absolute value of b is a positive integer. B is non-zero, so absolute value of b is a positive integer. I can cancel out from this inequality. I deduce that this integer, this non-negative integer, difference between q and q prime are integers. Therefore, the absolute value of q minus q prime is a non-negative integer, and it is strictly less than 1. But there are no integers between 0 and 1. The only non-negative integer which is strictly less than 1 is 0. Because absolute value of q minus q prime is a non-negative integer, and it is less than 1, I deduce that it is 0, which means I get that q is q prime. Now I can go back to this equality over here, say that q is q prime, deduce that the left-hand side is 0, and so the right-hand side is also 0, which means R is R prime. So I get that R prime minus R is b times this is 0, and therefore R is R prime. So we showed that the pair of integers q comma R is the same as the pair of integers q prime comma R prime, as we claimed. So this shows the uniqueness. Altogether, we have proved the long division algorithm. Now let's see what is the consequence of this to integers modulo n. But before we get to that, let's point out that q is called the quotient of this division and dividing a by b, and R is called the remainder of a divided by b. So we are essentially dividing a by b, and then we are getting this remainder, and we are getting the quotient q. Notice that here I'm not assuming that a and b are positive integers, and there is a subtlety when we are dividing by a negative integer. Please pay attention to this, work out some examples to understand this better. Okay, but let's see what kind of implication it has for integers modulo n. The next proposition shows that the cardinality of integers modulo n is precisely n. And all the elements of this set is the set of the residue mod n residue class of 0, mod n residue class of 1, mod n residue class of n minus 1, and all these residue classes are distinct, and therefore integers modulo n have exactly n elements. Here I'm assuming that n is an integer which is more than 1. Okay, so let's see why this is the case. Let's start with the first claim, that every element of integers modulo n is one of these, is a residue class of I, mod n residue class of I for some I from 0 to n minus 1. Okay, we start with an integer a, and I'm interested in the residue class of a mod n. So how can I get to the R? The key point is the following, that if I do long division, if I divide a by n, I get a quotient and a remainder. That means I get a pair of integers q and r, so that a is n times q plus r, and my r being a remainder is a non-negative integer which is strictly less than n, which means r is either 0 or 1 or n minus 1. Now, knowing that a is nq plus r means that a minus r is a multiple of n. That means a is congruent to r modulo n. Okay, so let's say it again. Because a is nq plus r, I deduce that a minus r is a multiple of n, therefore a is congruent to n modulo n. But we have discussed that a is congruent to b modulo n if and only if the mod n residue class of a is equal to the mod n residue class of b. So this relation implies that mod n residue class of a is equal to the mod n residue class of its remainder. Now r is either 0 or 1 n minus 1, which means the mod n residue class of a is in the set of mod n residue class of 0, mod n residue class of 1, mod n residue class of n minus 1. That means every residue class is among these n residue classes. So z sub n is indeed equal to this set. In order to show that cardinality of z sub n is precisely n, I need to show that these residue classes are distinct. I need to show that if I and j are two distinct integers from 0 to n minus 1, then the mod n residue class of I is different from mod n residue class of j. So again, we focus on the contrapositive, or we are using proof by contradiction. They are close to each other. So we are following it by proof by contradiction. I'm going to assume that I is strictly less than j, and both of them are integers from 0 to n minus 1. And I'm going to assume to the contrary that the mod n residue class of I happen to be the same as the mod n residue class of j. What can I deduce out of it? How can I reach to a contradiction out of this assumption? We have proved that mod n residue class of I is equal to mod n residue class of j precisely when I is congruent to j modulo n. That means that happens precisely when I minus j is a multiple of n and divides I minus j. But notice, j is a number here. Here, maybe I flip their order. It doesn't matter for us, so let's flip their order. So I'm assuming that j is strictly less than I. That's better. Now, knowing that n divides I minus j means that I minus j is a multiple of n, is an integer multiple of n. Q is an integer. But moreover, here I'm assuming that I is more than j, and therefore the difference I minus j is a positive integer, and because j is also non-negative, I minus j is also strictly less than n. Okay, so I minus j is a positive integer strictly less than n that happen to be a multiple of n. But how can that be? Let's pay attention, and this is exactly the contradiction that they were looking for. I minus j is nq is positive, and at the same time is strictly less than n. I divide all the sides by n. Remember, n is a positive integer, so it's okay to divide all sides of inequalities by n. It doesn't change the order. So after dividing by n, I end up getting that q, which is an integer, is strictly more than 0 and strictly less than 1. But there is no integer strictly more than 0 and strictly less than 1. That's a contradiction. And therefore, these residue classes are distinct, which means the set of integers modulo n have exactly n elements. Next, I want to define binary operations on the set of integers modulo n. So given two residue classes, I want to add them or I want to multiply them. Let's start with the intuition from odd and even numbers. We know that if I add two even numbers, I end up getting an even number. When I add an even to an odd number, I end up getting an odd number. When I add two odd numbers, I get an even number. Similarly, when I do multiplication, I can multiply an even number by any other number. Definitely, the product will be an even number. When I multiply two odd numbers, the product is definitely an odd number. These are the things that we've learned from elementary school. And the key point here is that I can treat the whole set of even numbers as a single element and the whole set of odd numbers as a single element, and define these operations plus and dot. I can say E plus E is E, E plus O is O, O plus E is O, and O plus O is E. I'm just taking the initial of odd and even. Similarly, I can say E times E or E times O or O times E. All of them are E. And O times O is O. So no matter what elements, no matter what even or odd elements you pick, you end up getting the same results. So you can treat these operations for the entire sets, and it will be okay. This is a point of view that we are going to borrow to define operations, binary operations, for integers modulo n. I'm repeating using the word binary operations. This is not something special. This is essentially a function that takes two values and spills out another value. Later, we will be expecting more out of these operations, and we will axiomatize the properties that we are looking for later. Okay, so the operations that we are going to define are as follows. I give you two residue classes, a residue mod and residue class of A and mod and residue class of B. I want to add them. But how can I do it? I simply add A by B. A and B both of them are integers, so I can add A to B. I get another integer, A plus B. Now I can look at the residue class of A plus B. I define the summation of residue classes of A and B to be the residue class of A plus B. Similarly, I let the product of the residue classes of A and B to be the residue class of A times B. Now, there are a lot of subtleties here. One has to be extremely careful in this kind of equation, in this kind of definition. Let me point out what are the subtleties. You see, this residue class, this notation, is not just one element, it's a set. The element A is an element inside this set. This residue class is an arithmetic progression. A is one of the elements inside this arithmetic progression. We say A is a representative of this residue class. So going back to biology, it's like saying that we are taking a particular mammal as a representative of all the mammals. So then we have to be careful that the thing that we are deducing out of this particular mammal is indeed true for all the mammals, and it's not just a particular property of this species. So whenever we choose a representative, do certain operation, or apply certain logic, we have to be extra careful that this process, we are not doing stereotyping. And the thing that we are deducing or claiming, it's actually true for all the entire equivalence class and not just for the chosen representative. Okay, let's go back to this particular setting again. This residue class, mod and residue class, is a set, and we are choosing this representative from this equivalence classes. In our mind, we are identifying all of them by the same thing, A. We are doing the same for the residue class of B. Then after choosing these representatives, we are applying this operation addition in Z for these representatives. Then we are claiming that this summation, the residue class that we get out of this summation, does not depend on the choice of the representatives. This is an important claim that one has to prove. This is exactly where we have to pay attention. Later in this course, we will be using the same idea when we want to define factor groups. So it's important to understand the subtlety over here, and as we will be a bit faster next time that we see a similar idea. So again, the point is that here we are using these representatives from this class and applying this logic or operations, and we have to be careful that we are not stereotyping, and our process is indeed independent of the choice of a representative from these classes. Okay, let's go to the proof of lemma. I think I've emphasized enough on the importance and the subtlety in the statement. Let's see logically how we can address this subtlety. So whenever there is this subtlety, we have to pick two different representatives and say that the process is independent of the choice of these representatives. So I choose A and A prime from the same residue class, and B and B prime from the same residue class. And my claim is that this process is independent of the choice of A and A prime, meaning the residue class of A plus B is the same as the residue class of A prime plus B prime. Or the residue class of A times B is the same as the residue class of A prime times B prime. So this process, these operations, are independent of the choice of representatives. This is how we phrase it. They are independent of the choice of representatives. Okay, so these are the equalities that we want to prove. We want to prove that under these assumptions, if A and A prime and B prime representative the same residue classes, then A plus B and A prime plus B prime, and A times B and A prime times B prime represent the same residue classes. Okay, let's start with hypothesis. We are told that this residue class is the same as the other one, which is equivalent to saying that A is congruent to A prime modulo n. As I've indicated, we often start with this side, at least in this class, we start with this side, use this translator, and get to integers and congruence relation. So knowing that these residue classes are equal, we deduce that A is congruent to A prime modulo n. That means A minus A prime is an integer multiple of n. So there exists some integer k where A minus A prime is n times k. I do the same for the other part of hypothesis. So the residue class of B is equal to the residue class of B prime, mod n residue class of B is equal to the mod and residue class of B prime. That's the same as saying that B is congruent to B prime modulo n, which is equivalent to saying that B minus B prime is n times L for some integer L. I am interested in A plus B minus A prime plus B prime. I want to show that A plus B is, okay, this is my goal. I want to show that the residue class of mod n residue class of A plus B is the same as mod n residue class of A prime plus B prime. But that one is equivalent to saying that A plus B is congruent to A prime plus B prime modulo n. And that one is equivalent to saying that the difference of A and B, A plus B, and A prime plus B prime is a multiple of n. So we are interested in this difference. We are told that A minus A prime and B minus B prime are multiples of n. How can I get to A plus B minus A prime, parentheses, A prime plus B prime? I simply add these two. So I add both sides. The left-hand side will be A minus A prime plus B minus B prime. I reorder the terms. I end up getting that this is A plus B minus A prime plus B prime. That's exactly what I'm interested in. But on the other hand, on the right-hand side, after adding the right-hand sides of 1 and 2, I get that it is nk plus nl. I factor out n, I get that it is n times k plus l. Again, k and l are integers, so their summation is an integer. That means this difference is an integer multiple of n, which means A plus B is congruent to A prime plus B prime modulo n, which is exactly what we needed. We do the same logic to show the other one. So let's see. Here there is an old trick that can help us to prove it. Introducing a middleman. Okay, so again, we want to show that mod n residue class of A times B is the same as the mod n residue class of A prime times B prime. Again, that means this is equal to this. If and only if A times B is congruent to A prime times B prime modulo n. And by definition, that means A times B minus A prime times B prime is an integer multiple of n. So we are interested in AB minus A prime B prime. Now, from AB to A prime B prime, so I have to change A to A prime and B to B prime. Instead of changing both of them at the same time, I'm going to change one of them at a time. So I go from A times B to A prime times B, and then from A prime times B to A prime times B prime. This is a type of technique that you've probably seen when you prove the product rule in calculus. But disregard that. Let's see the computation. A times B minus A prime times B prime. As I've indicated, we change these terms one at a time. That means I subtract A prime times B and add it. It means I'm doing nothing to the term AB minus A prime B prime. But this auxiliary term is going to help me actually. So as you can see, these two terms have B in common, so I can factor out B. And these two terms have A prime in common, so I can factor out A prime. But notice the hypothesis tells me that A minus A prime is a multiple of n. It's nk for some integer k. And B minus B prime is a multiple of n, is nl for some integer l. Now these two terms have n in common, so I can factor out n. And the rest are integers because integers are closed under addition and multiplication. So altogether, I end up getting that AB minus A prime B prime is an integer multiple of n, which means AB is congruent to A prime times B prime modulo n. That's exactly what we needed to show. That shows that the mod n residue class of AB is equal to mod n residue class of A prime B prime. Altogether, we get two operations on the set of these arithmetic progressions on this set of integers modulo n. Next, I want to show that these operations have nice properties. They are associative, we have distribution properties, and we have neutral elements with respect to addition and multiplication. Every element has an additive inverse, but maybe not every element has multiplicative inverse. Later, we will understand exactly what elements have multiplicative inverse. Okay, but let's start with the basic properties: associativity, distribution, what this means to have neutral elements, and so on. In this proposition, the formulation and the phrases are more important than the proofs. The proofs are rather easy and straightforward, but the phrases and getting familiar with the phrases are the key points of this proposition. So I give you three elements in the set of integers modulo n. Then both of these operations, addition and multiplication, on the set of integers modulo n are associative. What does associative mean? It means essentially I can remove parentheses in my computation. Parentheses are not needed. I can put them in whatever order I want and apply the operations. To be more precise, if I want to add residue class of A to summation of two residue classes, I can first add residue class of A to the first residue class that I've picked, and then add the result to the residue class of the third one. I can change the order of these operations, change the order of parentheses. Because the parentheses are not important in the final result, in certain computations, I do not put them at all. Because there is no ambiguity if I remove these parentheses. You can choose your the order that you wish and you like the most and do the computations in that order. The same is true for multiplication. When I multiply two residue classes and then multiply that result by, okay, so I start with residue class of A multiplied by the product of two residue classes, I can do it like that. Or I can first multiply the residue class of A by the residue class of B and then multiply the result by the residue class of C. So again, putting parentheses is not important. I can remove them. There is no ambiguity. Such a thing is called associative. So we say that these operations are associative. Both of these operations have neutral elements. Neutral elements means they do not have any effect, at least with respect to this particular operation. So for instance, when I'm adding 0, the residue class of 0 has no effect. It's a neutral element. So no matter what residue class you give me, if I add the residue class of 0 from both sides, I'm not changing it. I end up getting the same residue class. So the residue class of 0 is called a neutral element. For multiplication, the residue class of 1 is the neutral element. I said there is a unique one. We will be discussing the uniqueness later, but at least we are discussing the existence at this point. So the residue class of A, no matter what A is, times the residue class of 1 is going to give me the same residue class as before. And it doesn't matter what order I pick. So the residue class of 1 is the neutral element for the multiplication. As we can see, the neutral element depends on the binary operation that we pick. For addition, it's 0. For multiplication, it's 1 in this case. Now, every element has an additive inverse. Every element has an additive inverse. This means what? Every residue class that you give me, I can add some residue class and end up getting my neutral element with respect to the addition. The neutral element with respect to addition is the residue class of 0. Now, every residue class that you give me, I can add the residue class of negative A, and it doesn't matter what order I pick, and I end up getting the residue class of 0. Remember, I have to add A to negative A. I end up getting 0, so I end up getting the residue class of 0, which is the neutral element of addition. I have pointed out that the order doesn't matter. In fact, both of these operations are commutative, meaning it doesn't matter what order I add, I end up getting the same result. This is the case because the same property holds for the set of integers. A plus B is the same as B plus A. Set of integers is a commutative set with respect to both addition and multiplication. So the same property is inherited for set of integers modulo n. And addition and multiplication are also quite compatible with each other, meaning we have distribution. So we have distributive property. If I give you this residue class, when you want to multiply it by summation of these two residue classes, first you can multiply the residue class of A by residue class of B, and multiply residue class of A by residue class of C, and then add them. You get the same result. And you can do it from both sides. Of course, it's commutative, it doesn't matter, but let me emphasize that you can do it from both sides. So this is called distributive, from left or right. All of these claims are straightforward conclusions of similar properties from ring of integers, right, called ring from integers. In order to show you the flavor of the argument, I'm not going to prove all of them because they are rather easy, but in order to show the flavor of the argument, I'm going to go through only one of them. That's the distributive property, only one of the distributive properties. Let's see why this equality holds. As we go through the proof of this argument, you see how one can use these properties from integers and deduce these results for integers modulo n. Okay, so I want to start from this side and show that I'm getting the other side. Instead, I'm going to compute this side and compute the other side and show that they are giving me the same thing. So here I need to compute what is the residue class of A times summation of residue classes of B and C. So we start with this. Summation of residue class of B and C is the residue class of B plus C. You can think about this square brackets ends as kind of decorations. We are adding these decorations and then doing the computation in the integers. I can do these decorations at the beginning or at the end or at any step that I want. And because at the end of the day, I'm doing the computation inside the integers, I do have the distribution property. So I have distribution property after decorations as well. So that's the whole idea. Let's go through the details. So I take the residue class, sorry, this should be outside, the residue class of A mod n, and I need to multiply it by the residue class of B plus C mod n. By definition, this means I have to multiply these representatives and then consider the residue class of the product. And now I can use distribution property for integers, and that is A times B plus A times C, and then I'm taking the residue class of this. Now let's look at the other side of this equality. So I'm taking the product of residue classes of A and B, and I'm then adding product of residue classes of A and C. Now, what is this product? This is the residue class of A times B. What is this product? This is the residue class of A times C. Now I need to add these residue classes. Again, it means I have to add in the integers and then add these decorations. So I add A to B and A to C in the integers, A times B plus A times C, and then I take the residue class of this integer modulo n. That's the same as what we had before. This means that these things are equal. As you can see, the same argument goes through for all the other claims as well. But let's stare at this. We have defined these operations on this finite set of integers modulo n with n elements. These operations are addition and multiplication. They have nice properties. They are associative. We have neutral elements for both of these operations. We have additive inverse for every element. We do not have necessarily multiplicative inverse. That topic we will discuss later. These operations are commutative. I can change the order, and they are compatible with each other, meaning we have distributive property. So we'll come back to the range of integers and more properties of that and we discuss multiplicative inverses after we go through GCD, basic properties of GCD, Euclid's algorithm, and Euclid's lemma. So after we discuss those, we come back to the multiplicative structure of integers modulo for now.